Hi everyone. In this video, I'm going to explain about the realization of CMOS NOR gate. In the previous video, we have seen how NAND gate is going to be realized using CMOS devices like PMOS and as well as NMOS. Later, we have seen the operation of that NAND gate when the input condition is 0, 0, 0, 1, 1, 0, 1, 1. That means based on the input conditions. Now, here CMOS 2 input NOR gate realization we are going to see. CMOS 2 input NOR gate. So before going into CMOS realization, first let us see the symbolic representation of NOR gate. This is the symbolic representation of NOR gate with the two inputs like A, B and having the output Y is equal to R complement form. So A plus B whole bar. The same symbolic representation can also be expanded like this by separating the NOT gate. Okay, that means R followed by NOT is nothing but NOR gate. Same inputs A, B. Here we will be having A plus B. Now the complemented output is nothing but your NOR operation A plus B whole bar. Okay, so in order to construct this particular CMOS 2 input NOR gate, how many inputs are there? So we know number of inputs is equal to number of PMOS transistors and as well as number of NMOS transistors. Okay, so don't confuse, just by taking the number of inputs, if there are 10 number of inputs, 10 number of PMOS transistors must be used, and similarly 10 number of NMOS transistors must be used to realize this particular logic circuit in terms of CMOS. Okay, as here the number of inputs are 2, the number of PMOS transistors must be 2, and similarly NMOS transistors must also be 2. So 2 PMOS transistors and 2 NMOS transistors we are going to use now. Okay, but how to realize this? How to construct the two PMOS transistors, whether they should be connected in series or in parallel? And similarly with respect to NMOS transistor, how it is going to be constructed, whether they are in series or in parallel? See, I already told you in the last video, for product operation, the PMOS transistors in parallel. If PMOS is in parallel, for product PMOS in parallel. Okay, and for series, the same PMOS will be constructed in, we can say like it is for plus. For plus A plus B operation, for plus the PMOS transistors must be connected in series. This is fine, but with respect to NMOS realization, for product NMOS transistors must be in series, and similarly for plus realization, plus is for making the NMOS in parallel. Okay, now what is our design? A plus B whole bar, Y is equal to A plus B whole bar, 2 input NOR gate. Y is equal to A plus B whole bar means we are directly first constructing the circuit for A plus B, but due to the complemented action of the CMOS basic nature, the output is a NOR gate. Okay, so it is A into B. A plus B means we have to consider this case and as well as this case. So PMOS must be connected in series and NMOS must be connected in parallel. So PMOS devices must be connected in series and NMOS devices must be connected in parallel. Okay, so if you don't have any confusion in the realization, then only you can easily draw the circuit diagram. Now let us see how to realize the 2 input NOR gate. So the PMOS transistors must be connected in series as I mentioned, and NMOS transistors will be connected in parallel. This is NMOS transistor, this is NMOS transistor. If you are going to take this substrate terminal, for NMOS it should be outside. For NMOS it should be connected to outside, and here for PMOS, source and substrate connected together, arrow comes outside and here it goes inside, and here also arrow that comes outside and it is going inside for PMOS transistors. Otherwise there is another representation with bubble. Okay, that is also easy. Bubble if you are using means PMOS, if there is no bubble means NMOS. Instead of taking the substrate terminal, that is also another way. So it is VCC which is around 5 volts AB, and it is AB. Here is the place where we are connecting the output Y is equal to A plus B whole bar. Okay, so PMOS transistors are in series. Let us take the numbers of all the transistors. So there are 4 transistors. Now let us see what happens when, first condition, when A is equal to 0, B is equal to 0, then Y is equal to how much? Based on the truth table, let us take the truth table and we are checking now whether it is satisfied or not. So 0 0, 0 1, 1 0, 1 1. So 0 0 means A is equal to 0, B equal to 0, that makes the PMOS transistors on and NMOS transistors must be off. So this makes PMOS on, NMOS off for 0 input, because PMOS is connected in the reverse direction compared to NMOS. So PMOS in on state, on transistor will be replaced by a short circuit. So take an arrow mark like this. As they are in series, connect a series to arrow marks. Here it is the output, and here both are open circuited and they are in parallel. That means output is no way related to ground because both are becoming open circuited. This is Q1, Q2, Q3, Q4. So these are the transistors we have taken. Now as A and B are zeros, Q1, Q2 on, so output is equal to 1, logic high. Okay, and similarly, let us go to the another case. Second case, A is equal to 0 and B is equal to 1. Then what is the output? A is equal to 0, B equal to 1 means in the PMOS transistors, PMOS transistor Q1 is on, Q2 is off because B is equal to 1. And similarly, in terms of NMOS, Q1 is off, Q3 is off and Q4 is on because V is equal to 1. Okay. Now with this, let us draw the circuit diagram. Q1 is on means short circuited, and Q2 means off means open circuited, and Q3 is off and Q4 is on. Okay, on is nothing but either we can replace with a resistor or simply we can replace with a short circuited arrow. Okay, now see, output is connected to ground rather than connected to plus VCC because of the one of the transistors here is open circuited. So output is connected to ground. So output is equal to 0. So in the second case, when input equal to 0, output equal to 1, it is 0. Okay, and similarly, the next case also, A is equal to 1, B is equal to 0, Y is equal to how much? A equal to 0, B equal to, A equal to 1, B equal to 0 means these two cases will be reversed. Okay, and similarly here also it is going to be reversed. That's why the same output we will get here also. Coming to the last case, last case, that is A is equal to 1 and B is equal to 1. When both are 1s, what happens? Both the PMOS transistors are in off and both NMOS transistors must be in on. So both PMOS transistors are off and both NMOS transistors are on. So as NMOS transistors are on and PMOS transistors are off, there is no connection between output and VDD. It is two inputs only. So these two are connected in. So when A is equal to 1, B equal to 1, that makes the Q1, Q2 off and Q3, Q4 are short circuited. VDD, VCC. Okay, then what is the output? Output equal to 0. Output is equal to 0. Okay, so this is quite opposite with the truth table of NOR operation. That's why it is NAND gate. Here it is the complement of NOR gate. Complement of NOR gate. Okay, so in this way we can realize the CMOS NOR operation with PMOS and as well as NMOS. Okay, thereby we can see the operation of this particular logic circuit in individual cases, like when A is equal to 0, B equal to 0 and 0 1 1 0 and 1 1. Okay, thank you.